Hello, my name is Yoni Ziv. I'm Ecori Vice President of Business Development. I have around 20 years of experience in the industry in various R&D, business roles, marketing. I was in SolarEdge for 10 years. I was Vice President of Technical Sales. I opened a lot of market around the world. And today I'm working mainly in Brazil together with Ecori. And today we're going to talk about all kinds of things from the PV industry, starting with IV curves, which is the basic of the PV panel, which is the basic building block of our systems in our industry. In this training, we're going to talk about IV curve. IV curve is one of the basic models to represent the relation between current and voltage of any electrical device. We can see here some examples of resistors, a diode, a battery. Each one has its own IV curve, and also within the family of resistors and batteries and etc., each of the different models have different IV curves, which is pretty much like the footprint, the electricity footprint of the device. You can see a resistor, they have Ohm's law, linear relationship between the current and the voltage of the device, of the resistor. We can see a high resistance resistor, a low resistance resistor. We can see a battery which is not exactly straight line at the constant voltage. It has some slope because the internal resistance of the battery, and you can see a shape of a diode. These are all graphical representation of the mathematical physical description of the device relationship between current and voltage. Current is usually marked at I and voltage is used by V, and this is why the name is IV curve, current voltage relationship curve. The most interesting for us would be the IV curve of a diode, because PV panel, PV cell is basically a diode. Each cell is like a reverse connected diode. When photons hit this diode, electrons are freed and are generated. This is how the electricity is generated from the cell, from the diode. And the curve gives us a lot of information about the functionality and the best working point for this cell, and the cells connected together are the PV panel. So here is the more common IV curve, as you've probably seen, of a PV panel. It has a lot of parameters that are interesting, like the I short circuit, which is the maximum current out of the panel when both the plus and minus are connected together, are short circuited. You have zero voltage, but you have the highest current. And when you disconnect the plus and minus of the panels, when are disconnected from nothing, you have the maximum voltage, the V open circuit, but with zero current. If I have maximum voltage with zero current, I have zero power. If I have maximum current but with zero voltage, I also have zero power. I need to look for some point in the middle where the multiply of the current and voltage give me maximum power, because this is what really interests me. We're going to talk about this later when we're going to talk about MLPE and PPT, but you need to understand there are different points of power generation, starting from zero at the I short circuit and ending with zero at the V open circuit. The IV curve also depends on the irradiance and depend on the temperature. The higher irradiance, the more photons hit the cell and more electrons are generated, and you can see more irradiance, higher current. The voltage doesn't change much with the irradiance, only the current. And with temperature, I see that the lower the temperature, the highest the voltage. If I would only look at the voltage of a panel throughout the day, you could see that in the early morning and in the evening the voltage is a bit higher because the temperature is lower, and in the midday the voltage goes a bit down and the afternoon goes up again. So we have dependency beside the component itself. Is also dependent on the irradiance and also dependent on the temperature. In the case of PV panel, you need to understand that shade and dust and all these things are pretty much blocking the photons and are considered as reductions of irradiance. Again, in the morning and in the evening I have changes in temperature, and this also affects the power production of my PV panel. Here are examples from a data sheet. I took a typical data sheet and we look at the IV curve of a panel, and you can see exactly how the voltage change with the temperature and how the current change with the irradiance. You see different kind of irradiance for the same temperature and different power production, different voltages for the same fixed irradiance. One point which is very important in this information is the voltage temperature coefficient. Why is it important? Because many times I'm limited by the maximum voltage I can connect to an inverter or to an optimizer or a microinverter. And usually I just look at the V open circuit of the panel, but I need to take in account some addition of potential increase of the voltage in case of lower temperature. If I look at the typical panel temperature coefficient of the voltage, I will see something like minus 0.3, minus 0.4% per Celsius, percent per degree. That means that if, for example, I have the option in the area I'm connecting to go down in something like 20-30 degrees compared to the typical 25 room temperature degree of the standard test condition. For example, I can go to minus 5 degrees in a location where it's typically 25. I cannot just look at the V open circuit of the panel. I need to take in account reduction of 30 degrees. 30 degrees times minus 0.31 give me something like 10%. I need to increase 10% to the number of the V open circuit. So if, for example, I have a panel with V open circuit VOC of 50 volt, I need to take additional 10%, which is additional 5 volt when I'm considering the maximum V open circuit. Usually taking 10 to 15% increase to the number that you are calculating gives you a safe space for going down to the V open circuit at the lowest temperature. So we talked about IV curve, I short circuit, V open circuit, the maximum power point with the IMPP and VMPP, where I'm producing the maximum power of the panels, and when I'm calculating the maximum voltages, how to consider lower temperature by calculating with the voltage coefficient changing by the temperature. Thank you.